This afternoon, what I want to do is go through sort of a tutorial on writing an asyn port driver using the asyn port driver C++ base class. And this is going to be based upon a real device, which is a measurement. It's a sort of a multifunction device, USB, from measurement computing. It's this 1608 GX2AO, which is this little blue box right here. And this is a, well, you'll see. And what we're going to do is go through, and this device has, you know, sort of blocks. So it's got some digital I/O, it's got some counter timer, it's got analog input, analog output. And so what we're going to do is go through, you know, starting with baby steps. And so create a driver that only does one of those functions and, you know, is very simple, is like 100 lines of code, and then gradually add functionality to it until we get to the full-blown driver at the end. And, you know, that's a good way to approach any project, of course, is to start small, bite off little things, don't jump into all the complexity right away. Okay, so let me just say a little bit of word about these devices. So these are inexpensive data acquisition devices from this company, Measurement Computing Corporation. They've got PCI, USB, and Ethernet. As I say, this is a USB device. They're beginning to come out with actually a model that's very similar to this one that's Ethernet based, and I think that'll make them even more, you know, more useful in our environment, because USB is a little limited in terms of the length limitations of where the device can be relative to the computer. So these are just some of the examples of the devices that they've got. There's actually, this is an old slide. The one that I'm going to be talking about is this one, which is an $800, and you'll see it has a lot of functionality. I also, at this point, had bought a counter timer device, but it was based upon an old chip, and soon after I wrote this driver, they discontinued this device, but they've subsequently introduced a new device, and I do have a driver for that as well. That's in fact, it has a lot of the functionality of the Struck for doing multi-channel scaling and, you know, real-time pulse arrays. So this guy has got 16-bit analog inputs, you know, 16 single-ended channels or 8 differential channels. You can program the range of each channel. It can count up to a total of 500 kilohertz aggregate input rate. So if you're just running one channel, you can do it at 500 kilohertz, or two channels at at 250 or 8, whatever. It can be internally or externally triggered. It has an internal or an external clock. And input and output signals. It's got a 4K sample FIFO on board the device, and then it can stream across USB fast enough to keep up at this rate. And similarly, it's got two 16-bit analog outputs. Those can also be scanned, so you can load a waveform, and it will scan that waveform at up to 500 kilohertz. So it's like a, you know, a programmable function, an arbitrary function generator, or just simple analog I/O, analog output. Again, unlimited waveform length, because, you know, you just define it on the host and then it streams it across the USB. It's got 8 digital input-output signals, and they're individually programmable as inputs or outputs. A pulse generator with one output, a 64 megahertz clock, and 32-bit registers to divide that down, and you can set a programmable period, width, number of pulses, and polarity. And finally, a couple of counters, 2 inputs. They can count at 20 megahertz. They're 32-bit registers. But they're not preset counters. You can't set them to stop counting after a certain number of pulses, which is the functionality we generally want for a scaler at a beamline. In terms of the EPIC support, they provide a nice Windows library for all of their devices. In just a few calls, you get a lot of functionality. Some of their older devices have some Linux support you can find here, and a few of their new devices, including this one, have an open source message-based driver with support for Linux, Mac, and Windows. However, that driver is written in C#, and so to use it on Linux requires the mono compiler. I don't think you can call that from GCC or G++. Right. Since their C# driver itself is open source, in principle, it could be translated into C++. So for now, my drivers all use the Windows-only library, as will the example drivers to be presented here today. So this support is based on asyn port driver, uses standard asyn device support. The full-blown driver is 1,250 lines of code. It supports the digital I/O with BO and BI, long in records, a pulse generator, analog input, analog output with AO records. It also has a waveform generator support where you can load a waveform and have it output that waveform. It has some predefined waveforms. These are done in the Epix driver, not in the hardware, like a sine wave, a square wave, a sawtooth, pulse, random. You can control these kinds of things, the number of points in the waveform, the repeat frequency, the amplitude, and the offset after you define it. And then it has support for user-defined waveforms for an arbitrary waveform generator. So you could define your waveforms in an external application like MATLAB or IDL or Python and download them in a waveform record over channel access, controlling the number of points in the waveform and the repeat frequency. The waveforms are defined in volts. It's a 16-bit output, and a maximum is 500,000 samples per second. And the only limit on the number of points is the available RAM. It's got a waveform digitizer where you can control the number of points to digitize and the time per point and the number of channels. And it has a burst mode where you sample all the channels as close together in time as possible. Different kinds of triggers. You can have it be continuous or one shot. And again, that's the same pretty generous limitations on number of samples and so on. So in this tutorial, I'm going to present 5 simplified versions of the driver, building feature by feature. So in the first one, version 1, we'll just do 2 simple analog outputs. Then we'll add analog inputs, then digital outputs, digital inputs with a polar thread, and then pulse generator output with counter inputs. And then finally, the full version has all these, the waveform generator, the waveform digitizer, and trigger control. And let me just, to start off, I can just show you this is the MEDM screen for the full-blown driver. So this is the end product of what we're trying to do. And you can see it's busy. There's a lot of features in this thing that are being controlled by this driver. So let's start with the digital I/O. So we've got 8 digital I/O bits here, 0 through 7. I've defined the first 4, 0 through 3, to be inputs here, but I can change that. And the last 4 are outputs, and I've physically jumpered together here the first output to the first input, or 5 to 1, and I've physically wired 4 to 0 and 5 to 1 here, so that when I set an output, I'll read it as the input. So if I set this to low, you see channel 1 switch to low, and I set this one, and similarly that switches. There's also here a long in record that is similarly changing when I change these bits. And both these input bits here and the long in record are I/O interrupt scanned. So the driver is polling these bits in a polar thread and then doing callbacks when anything changes. For the analog outputs, I've got 2 analog outputs, That's what the device has. And then it has, since I'm using differential, it's got 8 analog inputs, and I've jumpered together the first analog output to the first analog input, and the second one to the second one. So as I adjust the analog output with this scroll bar here, you can see the input here is changing. Let's set it to a specific value, like 7. And similarly, I could change the second one here, and that's changing the second voltage up there. Set it to -5. Yeah. And we can control here, of course, the rate these records are scanning. For the pulse generator, you can set here the frequency or the period. You can set the width, an initial delay, the number of pulses to output. If you put 0, it just goes forever. You can change the idle state. Is that pulse line low or high when it's not counting? Not pulsing, I mean. And then there are these 2 counters, and I've taken the output of this single pulse generator, there's just one, and routed it with a cable into the first counter. So I can, if I reset that counter, and now I tell this is putting out 500 hertz, and I've told it to put out 2,000 pulses. So when it tell it to start, this should count to 2,000 and then stop. Unfortunately, they don't provide a way to ask, is the pulse generator done? Which is unfortunate. So here, I have no way, the software has no way of knowing that this is done putting out pulses. So I have to actually stop it and then start it again, and this will count another 2,000 pulses. And then I'm not going to go through the demo of the waveform digitizer or the waveform generator, but there's lots of capability here in terms of putting out a sine wave and changing its frequency and its amplitude. And this similarly with the waveform digitizer here, rapidly collecting analog input signals. So, okay, we're going to start with the version 1 of the driver, which is just going to have 2 analog outputs. It's going to have a single parameter, that drivinfo string we talked about this morning, which will be called analog out value. It's going to use the AsynPortDriver base class, and this entire version of the driver here is 131 lines of code. So it's pretty small. And so the the thing we have to do is we have to import, include AsynPortDriver.h, and we also have to include their header file. So cbw.h is the header file for the vendor library that comes from measurement computing, because we're going to be making calls to their library. I've defined just a driver name here, which I'm going to use in asyn print statements, so we can see what driver is generating the messages. This is where we're defining the string that we want to use as the drivinfo field on those records, or to define the parameter in the parameter library. A couple of symbolic constants. The number of analog outputs is 2. That's how many the hardware supports. And at this point, we're defining max signals. The number of addresses that this driver will support is going to be defined to be that same number, 2. So this version of the driver will support 2 asyn addresses. Okay, so this is now from the header file for this driver. So we're saying we're defining a new class here, USB 1608G, which is derived from AsynPortDriver, and it's got 3 public functions. The first is the constructor, which takes 2 arguments, the name of the port you're creating and the board number. The board number is something that you you figure out by running the measurement computing, they give you a little utility program, because you could have 6 of their USB devices hooked up to your computer, and it assigns each one of them a number, 0, 1, 2, 3, 4, 5, 6. So you got to tell it here which board of their library is going to be talking to. And then we're going to re-implement 2 of the methods from AsynPortDriver. The writeInt32 method and the getBounds method. And these are the parameters that those methods take. Then we're going to have some parameters that we could make private, or if you wanted this class to be able to be subclassed by some other class, you could make them protected. A protected data means that it can be accessed by derived classes of this, but not by anybody else. And then there's this, we're going to have some private data, which is the board number. So this is an argument into it, but we need to keep a copy of that. So we're going to put that into some private data. And then we're going to divide the number of parameters here to be the last. Okay, so what we've defined, here is we've only defined one parameter, this analog out value. Notice it's an integer. This is that integer index that we're keeping track of which parameter is which. This is a very simple version. There's only one parameter, so that is both the first and last parameter. And then we compute the number of parameters by the address of the first one minus the address of the last one plus 1. So that's just the simple way of computing how many parameters there are. And as you insert parameters into this list, you don't have to muck around with how many there are, except that you got to remember to have the last one pointing to the last one in your list and the first one pointing to the first one in your list. Okay, so here is the code for the constructor. So this is all it's doing here is invoking AsynPortDriver with the name of the port, the maximum number of signals that we defined to be 2 on an earlier page, the number of parameters, which is 1, and we're telling it here in the mask that this driver is going to implement AsynInt32, and it's going to implement AsynDrivUser. So we OR together those 2 masks. We're not doing any callbacks, so that parameter is 0. We're saying it's a multi-device because we support multiple addresses, and it can block because it's slow over USB. And auto-connect is 1, and we're going to use the default priority and stack size for the thread that Asyn Manager creates. And then this is saying this boardnum underscore boardnum means the private data in our class, boardnum, is going to be assigned to be the parameter that was passed into the constructor, boardnum without the trailing underscore. That's just a convention that people use sometimes in C++, that member data can have a trailing underscore, or some people put a lowercase m in front of the variable name to mean like mine. You just want some way of keeping track. Is this member data, or is it a local variable? Right. And it's good to have some sort of convention for that. Analog output. So now we're basically creating one parameter. We're calling AsynPortDriver create param. We say analog output string. That's that string we defined. It's an int32 parameter, and we pass it the address of that public or protected integer right here. And presumably what what AsynPortDriver is going to do is to assign this to the index 0, because it's the first parameter. But there's no guarantee of that, because the AsynPortDriver itself could be creating some parameters. Right now it doesn't happen to do so, but in the future it might. So that's why we're not assuming that this parameter index is 0, because this could be derived from some base classes which are themselves creating parameters before this one gets created. Okay, so now we need to implement, if we're writing an int32 for implementing the int32 interface, we want to implement the getBounds method. And basically, the analog outputs here are 16-bit devices. So we're saying that this takes two pointers to two 32-bit integers, the high and low values, the range of your device. And we're saying star low equals 0, star high equals 65,535, 2 to the 16th. And so that's all we have to do. So when Epic's device support for the AO or AI record calls us, it's going to get this. It's going to get this as the range of the device. Now, if the device is programmed in volts, you wouldn't need to do this because then it would be on the float 64 interface. But in this case, it's on the int. It's an int interface. Okay, so this is now the write int32 method that we're implementing in our driver. So when your Epic's analog output record processes, it's going to compute based upon the range of this device, 0 to 65,535, and the drive high and drive low fields of the analog output record. It's going to compute an integer, which it's then going to send to this driver to set the voltage, right? So it's going to pass us this AsynUser that Epic's device support created and connected to our driver for us, and then it's going to pass the value to be written to the device. So we've declared an integer address, and we say the function that we're going to execute is, or the function that's being described by this AsynUser is based upon the PAsynUser reason. And so the first thing we do is call this. This means it's an asyn. It's either in this class or it's in asyn port driver. GetAddress, and GetAddress is a method that is actually implemented in Asyn Manager, where you pass it a PAsynUser and it returns to you the address. So this is basically saying which of the two analog outputs are we talking to. So we got to get the address. We set that parameter in the parameter library for asyn port driver by saying set integer param, the address, the function, and the value. And then we say if the function is analog out value, which is probably true because we've only defined one parameter here. So if it's that, then execute a function called cbaout. Now this is a function from the vendor library. And it takes 4 arguments: the board number, which is that thing we passed in the constructor. This is probably board 1. Address, which we just got here. It's either 0 or 1. The way we want to program it, which is going to be, this is some symbolic constant that the vendor provide, because this device is a bipolar 10-volt device. So we say BIP 10 volts. And then the value. And the value here is an integer. So it goes from 0 to 65,535. Then when we're done with that, we say call param callbacks for this address. So if anybody has got a monitor looking, this would be like a read back of what the output voltage was. It's now going to get called back. In this case, it should be exactly what was passed in, but if it turned out that we did some check here that could have truncated or changed this value, then the callback would show a readback record in Epic's what had changed, what the new value really was, as opposed to what you passed in here. And then we do some checking and printing, status printing at the end. So if the status is 0, in other words, if this call worked, then we print a message using asyn trace.io driver. So this is a message that would normally not be enabled, right? So this is for debugging. And we're saying, port, this port name wrote this value to this address. So we just generate a message, giving the name of the driver, the name of this function, So that's a message that would be printed if you turned on AsynTraceIO driver for this port. And then if the status was not OK, it prints a message using AsynTraceError. AsynTraceError bit normally is set, so you would see an error message saying, there was an error writing to this address, and the status is, whatever this returned here. I mean, if this were a more sophisticated driver, we might have a table of error messages, that we build knowing what the status that this could return is. Or the vendor might even provide a library function that lets you translate an error return code into a more meaningful string. And then if the status is 0, we return asyn success, else we return asyn error. So if there was an error here, then the device support that called this, Epic's device support that called this, would have gotten an error return, and the record, would have gone into alarm, probably. Yeah, it would have gone into alarm. And you probably would have seen an error message also printed by device support. Okay, so then in order to be able to use this driver, I mean, that's the driver. In order to use that driver, we've got to be able to configure it from the IOC shell. So we have this is a C function that we define that is called by this IOC shell registration function here. And all it does is say, in fact, this should be changed. We don't even need to assign this. What this really should just say is new USB 1608G. And then, so it creates an object. It creates that an instance of that C++ class, the port driver we just defined, passing it the port name and the board number. And then here is where we define the IOC shell command. The IOC shell command is USB 1608G config, takes 2 arguments, a port name and a board number. This is where that IOC shell function calls the C function, which in turn creates the C++ object. This registers that function with the Epic's IOC. And this is what the DBD file looks for. Okay, so that's the driver. We've got to create a database to go with that. So here's a template file that all it is a single analog output record. It's set to PINI equals yes. That means when the IOC boots, it'll process this record and write a value to the hardware. It's an int32. I have to see what this does. I forgot. This is the output link. That's talking to the port and the address with that parameter we defined, analog out value, the driv user field. And then it's got a whole bunch of macro parameters it's going to take from your DB load records or DB, from a substitutions file. And we've said here linear. This is where this means it's going to compute an integer value based upon the drive high, drive low fields, and the full range of the engineering units of the raw units of the device. This is so that you could have this so it puts out an analog pulse instead of just an analog value. So there's a binary output record here that says, is it a normal output, meaning just a level, or is it a pulse? And if it's a pulse, this is the record that makes it go back to the return value when it's done. And we've got a couple of more records here that we stuck in to be able to tweak the value. So we've got a tweak up and a tweak down. So the user can click and make the voltage go up or down. And then this is the st.cmd file for that. So we create an application, a standalone application. It's got a DBD file, register record device driver, load the template file that I just showed you. A substitutions file that then loads that template file. And then this is where we configure the driver. That's the IOC shell command that we defined. Give it the name of the port and the board number. This is where we could set some trace debugging information. So this says set asyn, this is commented out, but if it were uncommented, asyn set trace mask, the name of the port, address -1 means all addresses. So set the debugging information for all addresses and set it to 255, which means turn on all debugging. There are not more than 8 bits in the trace mask right now. So 255 would turn on all debugging and IOC init. Oh, this is the substitutions file. So what I've loaded here is an asyn record that we can use for debugging, and then those analog output, 2 analog output records based upon the template file I showed you a couple slides ago, where we're setting the engineering units, drive high, drive low, engineering full, engineering low, hopper lopper, the precision, and so on. These are the MEDM screens that would correspond to that simple version of the driver. We've got an analog output, 2 analog output records. We can read back what the current value is. We can tweak them with these buttons here. This is the asyn record to be able to turn debugging off and on. This is a setup screen where we can change the drive limits in the engineering, conversion from integer to engineering units, where we can change it from normal to pulse output, and a top-level screen to load these with the right prefix and so on. Now, one thing that I didn't mention, but it's worth mentioning, is that the way that we've got a parameter list and asyn port driver for each address. So in this case, there's going to be 2 parameter lists, one for the first analog out and one for the second one. It's somewhat inefficient because often there's a whole bunch of parameters that really belong to the box, and then there's parameters that belong to each subaddress. And what we're doing is not distinguishing that. So there may be parameters that really only apply to address 0. The firmware version, for example, but we're duplicating that parameter for each subaddress. For the first and second and third analog inputs, they all have a parameter for the firmware, even though they probably don't need it, right? Because that's all the same. But it's simpler that way. There's just one type of, it's just n copies of a single list. Okay, so now what we're going to do in version 2 is to add 8 simple analog inputs, and we're going to add 2 new parameters. Analog in value, so that's the actual value of the analog input, and analog in range, because we can set the range of the inputs to be plus or minus 1 volt, plus or minus 2 volts, 5 volts, whatever. So we have 2 parameters that we need to worry about. And we'll also add a report function, so we can get a report out about our driver. And that increases it now to 197 lines of code, or adding these features added about 60 lines of code. And the way these slides work is that what's in boldface is what's new. What's not in boldface is what was in the previous version of the driver. So we just got a comment here. Now what we've done is define 2 new strings to define the drivinfo fields of the new for the new parameters, the analog in value and range. Defining a new symbolic constant, which is the number of analog inputs. We might as well define that to be the maximum number of analog inputs. It's going to be 8 or it's going to be 16. Whoop. So if it's differential, we have 8 inputs. If it's single-ended, we've got 16. We might as well define it to be 16. And the maximum number of signals now, instead of being 2, is going to be 16. So because we're going to need 16 different addresses that we support. And again, you can see that, we're defining a bunch of parameters. So we're having 16 different parameter tables, one for each address. It's a little bit wasteful because there's only 2 analog outputs. So those analog outputs are being, there's parameters for those in the remaining 14 tables that are not needed. So it's not very efficient, but we're talking about a small amount of memory, a few hundred bytes. Okay, so now we're telling it that we're going to implement another function, read int32, and another function, report. These are, again, virtual functions that are being re-implemented from the AsynPortDriver base class. And because we've said virtual here, they could be implemented yet again by some other class that wants to derive from this. And then here we've added those 2 new parameters into our protected data, the integer parameter numbers here. And we've redefined the last parameter to now be analog in range instead of analog out value. Everything else is the same. The constructor is still identical, except that we've now had to create these 2 additional parameters with the create param function. So analog in value string. These are also happen to be int32 parameters. And we are setting an analog. This is, a pointer to the parameter number that AsynPortDriver is computing for us. The getBounds function is now just adding into the test. It turns out these are also 16-bit devices. If these, if these were 12-bit A to Ds and 16-bit D to As, we would do this differently. One would go from 0 to 4095 and the other from 0 to 65535, but these also happen to be 16-bit devices. So in either case, we set the range to be 0 to 65535. In the writeInt32, so this is our writeInt32 function. It hasn't changed at all, even though you might think it should have, because we're implementing this new parameter that's called analog output range. So you might think that we would need to handle that case here because somebody's changed the range. Don't we need to talk to the hardware? Well, it turns out we don't, because you don't set the range when it's changed. You only set it when you tell it to acquire a value. And so we can just use the base class implementation, or actually that's not true. What we're doing is we're setting it in the parameter library. Analog output range is being handled here in terms of this call right here. It's being passed, we've got the function, and we set it in the parameter library, but we didn't handle it in the if statement because there's nothing special we need to do. What we did have to do is completely implement, this is all boldface, a new readInt32 function. So it looks similar to the writeInt32 function. We've got, get the function out of the reason, get the address, but now we're saying if the function is analog in value, then we're going and getting from the parameter library the analog in range parameter for this channel, this address, storing that in this variable range. And then we call their vendor library function cbain, board num, address, range, and then an address of where it gets the actual data. So you see we're passing the range here. So we didn't need to handle the range in the writeInt32 function because we're just getting the value out of the parameter library and using it in the call to their vendor library function. They want you to pass an address of a short, an unsigned short actually, but this wants an int, so we convert it from a short, unsigned short to an int, set that parameter in the parameter library. If we have any other functions, we could just call the base class method, and then we do call param callbacks on that address. So now, anytime this read function is called, it returns the value, by reading the hardware, and then it also sets the parameter in the parameter library, sets that value into the parameter library. So that's how we handle the analog inputs. And then finally, what we've got is a whole new function here to do report. So report is always called with a file pointer because, the asyn base library may have set it so that you're writing to a file. Well, you always are writing to a file. This could be standard out or standard air or some disk file or whatever. And then you're always passed an integer describing the level of detail that should be printed. As I said, if this is 0, you should print a very short message. So we come in and we say, fprintf to this file pointer, the name of the port and the name of the board number. And by default, that's all you get. If the details are greater than 1, then for the analog inputs, I'm looping and calling from the parameter library, getting the range of that input and printing out, channel 0, range is such and such. Then notice down at the end here, I call asyn port driver : report file pointer details. So this is our derived class's implementation of the report method, but we should always call the base class implementation, the asyn port driver implementation of the report function. So we'll get then that whole dump out of the parameter library. That we get for free. We don't have to implement that. Asyn port driver already did, as long as you remember to call the asyn port driver base class function. So we've added, we've got a new template file, analogin.template, with an AI record for the actual analog input value, and an MBBO record where we select the range. And in this case, their library is a little strange. So plus and minus 1 volt, actually, for plus or minus 1 volt, you tell their driver that the range is 4. If it's plus or minus 2 volts, it's 14. Plus or minus 5 volts is 0. Plus or minus 10 volts is 1. It's just where they get those numbers, I don't know. But so you associate, you have a string, but then you have an associated value. And because we're using the int32 interface, it's this value that's going to be sent to the driver. Now, if their device, let's say depending on which model we had of this, that these ranges were different, then we might not want to hard code these into the template file, but rather have the driver create this list of enum strings and enum values and have the record get them from the driver rather than hard coded into the database. And you can do that with asyn. It turned out, it wasn't necessary for this device. This never changes. Now we've got a substitutions file where we've added these lines for the analog inputs, the record prefix and record name, the port, the address, engineering units, a scan rate, and a precision for each of these analog input records. So that's what the MEDM screen is going to look like. You've got this is the readback value of that device. You've got a scan rate at which it's being read, or you can just press the read button here. This is passive. You could press read. You can create strip charts. If you press configure, you get this, and you can set. Here's where you could set the range for each of them, so they could all have different ranges, and then the display and engineering units. But we've made this so we still preserved our old version 1 analog outputs on the same MEDM screen. So now we're going to go to the next version, the third version of the driver, where we're going to add 2 digital outputs. So there are going to be two new parameters, digital direction and digital output. Because remember, for each of these digital I/O bits, you have to set a flag that says, is this an input or is this an output? So again, this is going to add about another 60 more lines of code than we had in the previous version. So this is beginning to look familiar, I hope. So we're going to define two new strings that define these two new parameters, digital direction, digital output. We set another constant, which is the number of I/O bits, which is 8. And we're going to implement one more function from AsynPortDriver, which is write uint32 digital. And write uint32 digital takes takes 3 arguments: the asyn user, the value, and an unsigned 32-bit value and an unsigned 32-bit mask. So the mask is saying, which bits in the output are you actually going to modify? Only the bits that are 1 in the mask. And we define the digital I/O parameters here. We just add more parameters to our list and redefine what the last parameter is. This should be boldface too. I changed that. Now we need to add another interface into our 2 masks here. So the uint32 digital mask gets added into the interfaces we implement, and it is now the only interface so far that's doing callbacks. We create these 2 new parameters with create param, so it's the same thing except that now it's asyn param uint32 digital. It's a different interface than the one we were using up above. Again, the address of that parameter in our protected data. And now this is the write uint32 digital method that we're implementing in our driver. Same kind of stuff we saw before. We go get the function from the reason. In this case, we don't need to worry about an address. Each of these bits is not a subaddress in the driver. There's just one. I mean, there could be, let's say, multiple 8 or 16-bit registers that we're writing to, and then we would have an address. But the bits are not addressed by an address. They're chosen through this mask. So if the function is digital direction, then we got to it says the output value here is going to be either digital in. This is a symbolic constant they define in their library, digital in or digital out. And then you go through the number of bits and you compare and you say, you have to look at the mask and one left shifted by I. If that's not 0, then you set this to be, you call config bit to set. Yeah, because you're basically saying this applies to a particular bit. And then if the function is digital output, you go get the parameter out of the library, which actually got set in the library up here. You're getting the direction out of the library. And so we're going through here. So we only write the value if the mask has this bit set and the direction for that bit is output, right? So we got 2 different things that control whether that we're going to actually set that bit. Is it set in the mask, and is that thing actually an output? Because we don't want to be writing to an input. So this is the logic that does that. But if those 3 things are, if this is true, that the mask and the outmask and the direction is not 0, then you call output that bit on this, what they call aux port. So this is, again, a vendor library function. So that sets the digital I/O. and then just the same thing. You know, printing messages if it worked with asyn trace IO driver, or with asyn trace error if it didn't work. So now we've got a template file for a binary output record here where we've got digital. So this is a binary output record that controls the direction. It's just either in or out. This is a binary, so that's a binary direction template. Here's a binary output template that you notice it takes a mask argument. And then this is a readback of the output with IO interrupt scan. So that's an RBV. That's not reading the input, it's just reading what was last written to the output. And then we can also have a long out where we write all the bits at once. So we can either have BOs, binary outputs, that write individual bits, or a long out that writes a set of bits at once. And this is a readback, again, of that long out with scan IO interrupt. So that'll be processed when that call param callbacks happens. A substitutions file, and you know, okay, so now these are the 8 binary output bits, and each has a different mask. So there's a mask of, you know, 1, 2, 4, 8, blah, blah, blah. So each of these is just a single bit in the register defined by this mask, which is what's being passed to the asyn uint32 digital write method. And this is the thing for the direction bits. So again, you have a mask, but this is using the binary direction template file instead of the binary out template file. And so this is now what we've got on our MEDM screen. We've got these direction bits. This is what I showed you in the demo before. So we've got 8 direction bits we can define for each bit as an input or an output. And then for the ones that are outputs, at least, we can define, you know, is it currently high or low? Or we can write to all of them with this long out. Now this would be a good example of where we should be using the output record callback function, which didn't exist at the time I wrote this. But if I set this bit to high, really the long out record ought to update to reflect that. And right now it doesn't. So it's kind of confusing because the long out and the binary outs are not internally consistent. But now we have the capability in asyn, well, when our 426 comes out in a couple of weeks, we will have the ability to do that. You can do it now with a database kludge. You know, we have things where you can make, you know, you put a few extra records in your database, and as long as this has a callback with a readback, then it can copy the readback value into the output record with actually doing the I/O, but that's ugly. It's much nicer to have it all done for you in the device support and not have to make a kludgy database. Okay, so now for the next version, version 4, next to the last, we're going to add digital inputs. So there's going to be a new parameter, digital input. And now what we're going to do is add a polar thread that reads these digital inputs so that the records themselves can have scan equals IO interrupt. When we did the analog input, you saw that we actually implemented the readInt32 method, right? So that those records were being periodically processed and going and reading the values with a real call to the driver. Here we're going to set up a polar thread that periodically reads them. The records don't need to be periodically scanned. They're IO interrupt scanned, so they automatically process if and only if there's a change to the output. And for digital IO, that's almost always what you want because they're usually not changing very often. So you don't want the record constantly having to poll, but you want a quick response when it does change. So this, again, added about another 60 lines of code over the previous version. We're now up to about 300 lines of code. So again, we're going to add a new parameter, digital input string, digital input. And we don't need to implement any new methods, any new methods from the class, but we do need to create a thread. And when you create that thread, Andrew could tell me if I'm wrong here, but when you create that thread with Epic's thread create, you're expecting to pass it the address of a C callable function, which I now want to invoke a C++ method in this class. And I think that means I need to make this public. And we got a couple of more, a couple of private data here, a number where we're holding the poll time. This is going to be how frequently we do the polling in our polling thread. And we've got a flag here saying if we want to force a callback. And so this is polar thread C, meaning this is going to be a function. This is a function that's declared with C linkage that we can pass to Epic's thread create. And then all it does is take this. This is a pointer to this. That's a pointer to this, but in order to invoke the polar thread from this C function, that's got to be a public function. Okay, so, and then in our constructor, we're just setting poll time to some default poll time, that constant that was defined, and set force callback to be 1, and we'll see what that does, what that's used for. So now we're going to create one new parameter, digital input string, and then we call, at the end of the constructor here, Epic's thread create. We're going to create, this is just the name of the thread. It's the low priority. It's going to be Epic's thread stack size medium. It's going to be this, we're passing this polar thread C function to it and passing this as the private argument to that C function. So this is the polar thread. So it is, was launched from Epic's thread create. It waits for the poll time. And so let's see, what's it doing here? So it's an infinite loop, just a while one. This probably, in good code, what this would have is we would have registered for a callback from Epic's that the IOC is being shut down. And we would have set a flag that says the IOC is being shut down, and this would have exited had it detected that that flag is set. Because this could lead potentially to the application crashing during the IOC exiting if this tries to access memory that's already been deallocated or something. But we didn't do it that way, so you might get an error message when you exit the IOC. So what this is doing is taking, okay, so this is important. So this, remember, this is now running in a separate thread. And when all of, and I haven't had to talk about mutexes or locks up to now, but what you should know is that all those functions that we've been executing, like writeInt32 and readInt32 and stuff, remember, they've been called from device support making C calls to asyn manager, which then finally got turned into C++ calls to your driver, your asyn port driver. Hidden to you was the fact that each asyn port driver, each asyn port driver object has a mutex that has been taken when those functions are called. So they're protected against anybody else being called by that mutex, by conflicts by that mutex. So you don't need to worry about it in those functions. The fact that that lock has been called, and when you get out, when you exit, unlock will be called. But if you write your own thread, you do need to worry about that. So anytime you're accessing class data, including the parameter library, you need to have the lock taken. So you just do that here by saying lock. So that now takes the lock. Now you're doing, what we're doing here is reading, this is their vendor library function to read a digital input, print a message if it didn't work, and now it's doing some, some logic to say which bits have changed, because we only want to do callbacks on the bits that have changed. So we have to remember what the previous value was, but the very first time this runs, we won't know a previous value. So we say if we force a callback or changed bits is not 0, then we take the new value, make it the previous value, do a force callback, reset force callback to 0, and then call set uint32 digital param with the new value. And then loop over the number of signals, call param callbacks on those values, and then unlock. So now, everything we were doing here was done with the mutex taken, with the lock, but now we call unlock and epochs thread sleep poll time. So now this thread is sleeping for some short amount of time without the lock. If you forget to do that, your IOC is hosed, because nobody can write to this. All the records will block because they can't get at. They'll be calling lock, and you haven't released the lock. So basically, the general rule is the only time you call unlock in one of these threads is when you're sleeping or you're waiting for an epochs signal, or epochs event wait, something like epochs thread sleep or epochs event wait. You could call unlock, or in the case of like the area detector plugins that are doing really computationally intensive tasks, what they need to do is to put those computationally intensive tasks in a block of code that uses only local variables. And then so they can do that with the lock released. So now that thread can be running without blocking anything else for that computationally intensive stuff. And only when it's done with the computationally intensive stuff, take the lock and start putting things in the parameter library. So this is the binary input template. So it's just a BI record with digital input. And we also have a long in, so we can read all the bits at once into a long. Substitutions file loads the long and then loads each of those bits again with the separate masks. And now we can implement these inputs, which are being read by that polar thread that we just looked at, setting both the individual bits and the value of the long. Finally, get to the last version, sort of the last simple version of the driver, and I'm not going to go through the full-blown version of the driver. So this added basically support for the pulse generator output and the counter inputs. So there are 8 new parameters, run the pulse generator, set the pulse period and pulse width and delay, and then the counter value and counter reset. So what we're going to do is to do those counter inputs are going to be polled in the same polar thread we just wrote. So in addition to polling the binary inputs, we'll poll the counters. So they're going to also be scan IO interrupt, and this added like 170 more lines of code than we had in the previous version. Again, this is going to start to look very familiar. In fact, I don't think anything has changed on this page. Here's the strings that define, so there are quite a number of parameters, 6 parameters that control the pulse generator and a couple of parameters for the counters. And then we have to define some more constants here that have to do with the minimum and maximum frequency and the minimum and maximum values that you're allowed to use for the delay. These just come from the documentation for the device. The number of counters is 2. Again, we just add those parameters to the into the list of protected member data there. And then we're going to actually add, remember we had some private data in the past, the board number and the poll time and forced callback, and now we're actually going to write 3 private functions, methods, or no, actually 2 methods and 1 more piece of data to implement the pulse generator. So now in the interfaces that we implement, we're going to put the int32 mask and int float64 mask for the interfaces that can do callbacks. And we're going to create the parameters for the pulse generator, create the parameter for the counters. That's it. Okay, so now here's the code to actually start the pulse generator. This is what's going to be called when the record that says start on the pulse generator gets processed. So what it does is there are a whole bunch of parameters that control the function of the pulse generator: the period, the width, the delay, the count, and the idle state. And we just go get those parameters. 3 of them are doubles and 2 of them are integers. We just go get the values, the current values of those, out of the parameter library. Those were, updated by a write float64 operation or a write int32 operation. Then we're doing some calculations here on the duty cycle and the period, because I think what I wanted to expose to the user here was the period and the width, but their software thinks in terms of duty cycle. So, I had to convert it to duty cycle, and then you just call CB pulse out start, the frequency, the duty cycle, the count, the delay, and so on. That's just calling the vendor function again with some values that we've either read directly or derived them from some other numbers. And okay, so this is important here. We may not have gotten the frequency, duty cycle, and delay that we asked for, because their library, you can ask for a certain duty cycle, but it may have a precision and it can't give you exactly what you asked for. So what we is that right that I'm reading it back? No, these are just computing the values based upon, to make them internally consistent, and then it sets back the actual value of the pulse generator period, width, and delay based upon what we actually told the hardware to do, so that you can get a readback that says, you asked for a delay of this, but you actually got this modified by delta, or you asked for something that was outside the valid range now. And then we've got another function that we implement that's just to stop the pulse generator when the user presses stop. So in write int32, now the pulse generator function, so if the function is pulse generator run, then if the value is true, start the pulse generator. Else, if the value is false and it's already running, stop the pulse generator. And here's what we want to do is that while it's running, the user might modify the count or the idle state. And so if it's running, stop it and restart it. When it restarts it, remember it goes and does get double param or get integer param for these things. So now it's going to stop it and then restart it with the new values of the parameters without explicitly passing them to this function. It's going to get them out of the parameter library. Oh no, here I actually was implementing write float64 because what I wanted to do was, if you changed the period or the width or the delay, I want to stop the pulse generator and restart it. But there's your question. It's been set in the parameter library right here. So it's done before we do the guts of the code of this function. Now sometimes, and that's generally the way I've been doing it, is to always do the first thing you do is to set the value in the parameter library. Sometimes your code executes and you realize, whoops, I shouldn't have done that. You know, something went wrong, and it didn't actually take that value. So now, you know, you can undo that by later on putting the value back to what it used to be. You know, so you might, in some cases, you might need to cache the old value in case you need to reset it because the new value didn't take for some reason. You know, like your device is offline, whatever. Okay, so in the polar thread, now all we're doing is in the polar thread, in addition to reading the digital inputs that we did last time, we're now going to read the counters. And, you know, this is pretty simple. We just read the counter, and then we call set integer param counts, count value, and then down at the end of this function, hopefully, yeah, it's going, you know, I equals 0 to max signals, call param callbacks. So, you know, if you've updated a new value of that counter here with set integer param I, it's going to do the callbacks. So the records, they're probably long in records for those counts, will be IO interrupt scanned. So we've now got you know, a BO record to start and stop the pulse generator. We've got an AO record, which is float 64 to set the period of the pulse generator. We can also set the frequency, but this is, you know, frequency and period are there's two different ways of describing the same thing. That's just done in the database. The driver doesn't have to worry about both. The driver only knows about period, but if you change the frequency here, it'll calculate the period, and if you set the period, it'll calculate the frequency, because sometimes, you know, sometimes users like to see both. Similarly, the width, that's implemented directly, float 64. A delay, again, implemented directly, float 64. This is a long out that says pulse count and pulse idle state. Oh, right, this is how many pulses you want to output, and this is the idle state. You know, is it high or low when it's not pulsing? For the counter, right, we've got a long in. That's the counts. It's IO interrupt scanned, and a BO record that resets the counter back to 0. Substitutions file, just loading the pulse generator and the counter. Template files we just saw. And so now it looks like this. You saw this on the demo at the beginning of the class. So we've got the pulse generator records here, and the counter records here. Okay, so in the full released version of the driver, which I showed you at the beginning, the things that we haven't done in the first 5 versions here are the waveform generator with predefined and user-defined waveforms, 8-channel waveform digitizer, trigger support. So that altogether added 42 new parameters and, you know, brought the total number of lines of code up to 1,200 and something. So it's like 770 more lines of code than the previous version, because these are fairly complex things to worry about. But, you know, with a driver of that size, you're supporting basically all of the features that this device has. And that's the screen you saw before that has all those features on it. And so, you know, being able to implement that level of complexity in only 1,200 lines of code is actually pretty good, I think. Because a lot of the stuff is done in the base classes and by ASYN itself. And one of the restrictions that ASYN port driver forces on you that ASYN doesn't is that we've said that each one of these driv user strings, or, you know, pasyn user reasons, is associated with a specific interface. And ASYN doesn't have that restriction. You know, you could use the same string and have it, you know, be both implemented both on the float 64 and int32 interface to do different things. But the parameter list in AsynPortDriver doesn't allow you to do that. Each parameter is one string. It's got to be unique, and the interface, only one interface for that string. It's not a big limitation, but it's something to be aware of. I haven't ever found it to be limiting, because typically something's an integer or it's a float, and it's not both.